Well, thank you. It's my pleasure to be back in South Korea. I really like the food and people and everything. So, so last summer I gave some lectures about mapping class group, and these are going to be very different because I don't really work on random walk myself, or at least not yet. But last fall there was a program at MSRI in geometric group theory, and it became very clear that that the probabilistic methods are going to become more and more important in geometric group theory. So I decided to learn some of it, and now I'm sharing that with you. But I'm by no means an expert, and feel free to ask questions. I like audience participation. So if something is confusing, just ask. Okay, so let's start with what is random walk? Okay, so the setting is that you have a group, and it will always be a countable group. It doesn't have to be finitely generated, but it should be countable. Countable group, and then we're going to have a measure, a probability measure on it. So mu is going to be a probability measure on G. And the basic example that just, very classical is that when the group is Z, and then the measure is going to assign, so the measure of number 1 is going to be a half, and the measure of -1 is going to be also a half. Okay, and at 0 on all the other group elements. So this is known as Drunk's walk. And so what happens is that you think of the group as this. So these are integers, and 0, 1, 2, 3, and so on. And what this means is that at every time interval, the drunk that starts at 0 flips a coin and decides whether it wants to go to the right 1 unit or to the left 1 unit. And this is done with equal probability. Okay, so the random walk in this case will produce a sequence of integers. They're all going to be 1 or -1, but they could be something like 1, -1, 1, 1, 1, -1, etc. And to a sequence like this, you're going to associate a path in the group, right? So these paths are called sample paths. Okay, so I'll define them in a minute. And these, in this case, these sample paths are just partial sums, right? You start at 0, and then at the first time period you did 1, and then you did -1, so that means you went back to 0. So this is kind of the sequence of locations after a certain number of moves. Okay, so then you're again at 1, and then you're at 2, and then at 3, and then back at 2, and so on. Okay, so that's that's what the sample path is. Okay, so let's make something a little bit formal here. So we're going to we consider G to the positive integers. Okay, so Z greater than 0, this just means positive integers. So this will correspond to sequences like this, right? So this is going to be an element of this group G to Z greater than 0. So just a sequence of in this case, coin flips. Okay, and then and we're going to equip that with the product measure, if you want. So equipped with the product measure. Okay, so what I mean by this is that this is the space here has it's a measure space, and to define the measure, I just have to define it on cylinders. So I take something like the measure on let's also call it mu. Maybe that will be confusing, but that seems to be the standard practice. So I take a basic set in here. This is going to be this is called a cylinder, G1, G2, G say n cross G, Z greater than n. Okay, this is called a cylinder set. So what is the probability that your sequence of coin flips starts with a particular sequence of elements? G1 through Gn. It's a particular sequence of 1s and -1s in this case. Well, this is going to be just mu of G1 times mu of G2 and so on times mu of Gn. Right? It's the probability that you get G1 on the first flip and you get G2 on the second one and so on. Okay, so this formula defines a probability measure on this product. Okay, now what we're really interested in is the space of sample paths. So this is going to be omega. Omega is going to be the space of sample paths. And as a set, it's actually exactly the same as this. So this is the G to Z. Well, I don't know whether they want to start at 0 or not, but anyway, this is usually greater than 0. But you shouldn't think of it as the same space because the measure will be different. Okay, so we have a function. So have a function that goes from G to omega, and what does it do? Well, it takes a sequence of these coin flips and assigns the sample path, and this is going to be, the G1. We really like to start with 1. So then G1. This is the initial location, the identity in the group, and then G1, and then G1, G2, and so on. Right? You take all these compositions. Okay, so that's a certain function. And then what is the probability that a certain collection of these sample paths occurs? What is there's going to be a certain measure on omega. So the measure on omega is the push forward of mu. Right? I have some measure on this space, and then I have this function, and I can push forward the measure, and I'll get the measure P. Okay, that's also a probability measure. And now, how does this, more concretely, what is the measure of a cylinder set? Let's say I take 1, G1, G2, G1, Gn, and then, I should say, and then cross Z to greater than n. What is the measure of that cylinder set? Well, it is the measure of this cylinder set, right? So this is going to be mu of G1 to mu of Gn. The probability that you get a path that starts just like this is the same as the probability that you have exactly this collection of coin flips, G1 through Gn. Okay, so that's what random walk is about. So you want to study this space omega, right? So maybe.
마음이 이미 열렸겠다.
Yeah, so there's something called the law of large numbers. And I'm just mentioning this because it's a very classical thing related to, say, Drunk's walk. So you consider so in Drunk's walk, you consider the function Sn. This is going to be this omega n divided by n. So you look at the position of the random walk after time n, and you divide by n. So this is somehow, if you're hoping that your random walk is going to infinity with linear speed, then this omega n over n should be some positive number, or a negative number. But then something that's not too close to zero. But in fact. Okay, so then, this in fact this converges to zero, almost surely. Okay, so this terminology almost surely means that for all, so this makes sense for any sample path. For any sample path, you can compute omega n over n, and you can see if it goes to zero. Well, on the set of measure 1, on the set of full measure, it goes to zero almost sure. So this is on the set of full measure in omega. Okay, so that's what's called the law of large numbers. And then there is a fancier version of this called the central limit theorem. You can ask, how? So maybe it goes to infinity, but very slowly. But then what's the, you can ask finer questions. How fast does it go? And the central limit theorem just tells you that, if I take square root of n times Sn, so as I said, you should think of Sn as going to infinity after time n. The distance from the origin should be on the order of square root of n. So square root of n times Sn, this is like omega n divided by square root of n. Okay, so that should be some number that's reasonable. That's somehow, it should go to some. It shouldn't converge to zero, for example. And so what you know is that this converges in distribution. Okay, to in this case to 1 over square root of 2 pi times e to the minus x squared over 2. And this is the normal distribution. It's some kind of a bell curve. It looks kind of like this. This is roughly 0.4. And so what that means is that if you give yourself some interval here, let's say this interval, and maybe if you take the integral of this function and you see that that's 99% of the integral on this interval is maybe 99% of the integral of the whole bell curve, which is 1. Then the probability that this square root of n times Sn belongs to that interval is going to be 99%. Okay, so this is somehow, maybe more formally, this in distribution, what that really means is that these functions Sn, they're functions from our space of sample paths omega into R, and so you can push forward the measure that you have on the space of sample paths. And as n goes to infinity, these measures will converge to the measure given by this bell curve. Okay, that's sort of a classical thing. Okay, but that's not what we're going to do. What we're going to be concerned with is random walk in hyperbolic spaces. And let me maybe state the main theorem. Okay, so So his goal is going to be to prove the following theorem. So this is the theorem of Marr and Tiozzo. Okay, so G is going to be a countable group of isometries of a delta hyperbolic space X. And mu is going to be a non-elementary, so we'll have to explain what that means, non-elementary probability measure on G. Okay, so maybe I'll say it here. So what does non-elementary mean? Well, so I can look at the support of the measure. So you can look at the set of elements whose mu is non-zero, right? So look at the support of mu, right? That's the set of G's in G, so that mu of G is positive. And then I can look at for example, I can look at the subgroup generated by the support, and I would like that to be the whole group, for example. But more generally, I can look at the semigroup support. Here we are really, when we do random walk, we are multiplying the group elements, not really the inverses. Okay, so I can look at so this is the semigroup generated by, so just products of these elements without taking inverses. Semigroup generated by the support. Okay. So what I want is that this thing contains a loxodromic element. And does not leave a finite set in the Gromov boundary of X invariant, and no finite subset of the boundary of X. So this is the Gromov boundary of X is invariant under this, is sup mu invariant. Okay, so those are the assumptions. So for example, this rules out the Drunk's walk. I mean, the group Z, of course, is hyperbolic, and it's acting on a line which is hyperbolic. But this last condition will not hold, because the boundary consists of 2 points, and that will be, of course, invariant. Okay, so I'm not allowed these kinds of simple walks. It has to be something more complicated. Okay, so then for any x0 in X, so this is the base point, right? If I have a base point in X, so here's my X, then what I can do is I can think of the orbit map. So x0 corresponds to the identity in the group, but for any other group element, I have a translate. So if G x naught, I have over here. So instead of thinking about the random walk in the group G, I can project it to X. Right? I have an orbit map. So G goes to here. This is the orbit map that sends G to Gx naught. Okay, so you can think of G as sitting inside X, as some kind of a countable subset. And the conclusion is that for any x naught in X, the base point, almost every sample path and now I'm projecting it to X. So it's not just omega n, but I'm applying omega n to x naught. Okay, for n in n converges in X union boundary X to a point in boundary X. Okay, so I take my typical sample path, and I'll get some kind of I'll get a path like this, and it will be converging to a point in the boundary of the Gromov boundary of this hyperbolic space. And that's very different from from Drunk's walk or from these classical situations. There is no reasonable space, even for like z to the d. You might think of a boundary as being some kind of a sphere out there, but a typical random walk, sample path, is not going to converge to a point in the boundary sphere. It'll be wiggling around too much. It's not going to converge anywhere. But in hyperbolic spaces, the situation in some sense is much nicer. Okay. So why is this? But by the way, there is a lot more in their paper. I think since we only have a limited amount of time, I'm going to focus on this theorem. They also show that under, say, mild hypotheses, this convergence is linear. That is, there is some positive constant, so that if you look at the location of your random walk after n steps, the distance from x0 is going to be, with large probability, it's going to be this positive constant times n, at least. It'll be bounded away from. So in other words, the speed is positive. The speed at which you're going to infinity is positive. This is called the drift. Okay, it's positive drift. So again, that's very different from these classical situations. Okay, so maybe as the next thing, I want to give a little outline of the proof, and I guess that's going to also tell you what the next few lectures are going to be about. Okay, so are there any questions? All right. Okay, so let's talk about the outline. Oh, maybe first I should say, just a little bit of history here. So what are some examples? Examples are, so G could be a hyperbolic group itself. G is a hyperbolic group. And then X could be equal to G. In other words, you can have a hyperbolic group and then you're looking at the random walk of the group on itself. And then the theorem is just saying, this non-elementarity, the condition that it's non-elementary, just somehow corresponds to the assumption that G itself is non-elementary, and maybe that this measure, maybe the measure generates the whole group or something like that. Okay, so there are some mild conditions on the measure, but in this case, this was actually a theorem of Kajmanović in the 90s. So this was Kajmanović in the 1990s. Okay, so in that case, this theorem is not new, but it is, in fact, very important in geometric group theory to allow spaces X that are not necessarily locally compact or locally finite, and to allow group actions that are not discrete, for example. Here, there's no assumption about the discreteness of the group, of the action of the group on X. And since I'm a fan of mapping class groups and out Fn, I want to point out that those kinds of situations arise very naturally in those groups. Okay, so for example, you can take G to be the mapping class group. Sigma. So this is the mapping class group of a surface sigma, and then X could be the curve complex. So this is the kind of thing I was talking about last summer. Curve complex of sigma. This is hyperbolic, delta hyperbolic. It's a theorem of Mazur and Minsky. And this group is acting by isometries, and it's not discrete. The reaction is not discrete. The space is not locally finite. You can think of it as a graph if you want. Even though I said complex, but what matters is the one skeleton. but then a vertex is going to have infinitely many neighbors. And so so these classical this Kajmanovic kind of work wouldn't apply here. And then I'm also a fan of out-fn, so G could be the automorphism group of a free group, outer automorphism group of a free group, and then X could be, for example, the complex of three factors. There are actually several choices here, but let's just say this one. So a vertex here is a conjugacy class of non-trivial free factors in Fn, and then you put an edge between two of them if one contains the other. Okay, so and then the same discussion applies. So X is not locally finite; it is hyperbolic, and you have this action. In both of these cases, the boundary is understood. So we know. So in these cases, we know. So we understand boundary of X, the Gromov boundary of these objects. They're described in terms of some the spaces of measured laminations on the surface, or in this case, spaces of actions on arteries. And in fact, I'd like to get to applying this theorem to these situations, or at least to mapping class groups, if I don't run out of time. But the application is going to be applying this machinery in these two situations. So this was observed by Horbez, that you can apply random walk to prove a classical theorem about mapping class groups. So this was a theorem of Ivanov in the case of mapping class groups. Ivanov, he gave a classification of subgroups of mapping class groups. So if I take any, so if H is any subgroup of the mapping class group, then one of the following holds. So it could be that H contains two independent Pseudo-Nosov homomorphisms. Okay, so maybe I won't discuss what this means. This was what we did last summer. You're supposed to remember that, or to those who were here. But you should think of these as being generic. These are generic elements of the mapping class group. That's one. So the second possibility is that H is virtually cyclic and generated by Pseudo-Nosov. I mean, once you pass to a subgroup of finite index, which is Z, then the Z is generated by Pseudo-Nosov. And then 3 is that H virtually fixes a curve, a simple closed curve. So it's reducible somehow. So this is a generalization of Thurston's theorem about the classification of individual elements of the mapping class group. And it applies to all possible subgroups. And what's surprising is that the theorem, the statement doesn't involve random walk. And the classical, the original proof of Ivanov is, it's hard work, but there's certainly no random walk in it. But somehow, with this machine, I'm not saying that the proof is going to be easier, because you have to, you have to understand this machine here, and you also have to, understand a little bit about the curve complex and so on. But those are now somehow standard techniques. And so the point is that with these standard techniques, this proof becomes easy. While the original proof is still hard. I mean, even it's not. The techniques are not all that standard. Ivanov's techniques are not all that standard. It's hard work. Anyway, I thought that's an interesting thing. And then there's also a comparable theorem for out Fn that's due to Handel and Moser. Okay, so it tells you about subgroups of out Fn, and it's a similar classification. And it can be proved in the same way. All right. Okay, so let me now go talk about the sort of outline. Oh, there's one more. Yeah, one more situation where this applies. This is that's number 4. So in geometric group theory, people study cat-zero cube complexes. And to every cat-zero cube complex, you can naturally associate a hyperbolic space. So if you have a random walk on a group that naturally acts on the cube complex, then you can also consider this associated hyperbolic space and random walk on it. And then this theorem will tell you about it. Okay, so this is number 4. So G is a group acting on a cat-zero cube complex. Okay, so then you can consider X. So let's call this cube complex Y, and let's say X is the contact graph of Y. Okay, so what is a contact graph? So if you have a cube complex, then there's a naturally associated graph. So first of all, you can talk about hyperplanes. Any cube complex has a hyperplane. So what is a hyperplane? Every cube. So does everybody know what a cube complex is? No? Should I say what it is? So it's just it's like a simplicial complex, but it's made out of cubes instead of simplices. And this cat-zero refers to the condition. This is a non-positive curvature condition. So it just means that whenever you look at the vertex and you look at the link. So in this case, you look at so here's the link. And, the link of this vertex has 1, 2, 3, 4 vertices, and then there are edges for the corners of these squares, and then there will be triangles for the 3 cubes that are attached. And this cat-zero condition just means that that every link is what's called a flag complex. So that means that so whenever you see the boundary of a simplex in the link, then the interior is also in there. So in other words, it's determined by the one skeleton. You look at the one skeleton, and then whenever you can fill in a simplex, you do. So, for example, the boundary of the 3 cube, so boundary of the cube, is not cat-zero, because if I look at this vertex and I look at the link is going to be just a hollow triangle. Well, that's not allowed, right? Because you see, this is the boundary of a 2 simplex, but the 2 simplex is not there. You're somehow forced to put the cube in, and everybody knows that the 2 sphere is not non-positively curved. So that's why this condition is natural. So this is Gromov's flag complex condition. This another sort of funny way to state this condition is that every non-simplex contains a non-edge. Kind of have to think about what that means, but here's a non-simplex because it's not a simplex, it's just a boundary of a simplex. So it must contain a non-edge, but that's not true here. It contains all the edges. Right, so okay, so it's a sort of a joke, but it's a correct definition. Every non-simplex contains a non-edge. Okay, so that's what a cat-zero cube complex is, and then there are hyperplanes. So given any cube, you can talk about there is a hyperplane of this. It's a cube of codimension 1 that cuts it in half. So a square is going to have 2 of them. A cube is going to have 3 of them. Right? And then what's a hyperplane? Well, I have to extend. I start with one of them, and then I have to extend. So if I take this, then I have to since I already have this point in this 3 cube, then I have to extend it to include the next this mid cube. These are called mid cubes. Okay, so if I had other cubes hanging off of here, then I would have to keep extending and so on. So these are called hyperplanes. Okay, so this one, I'm just, we won't really be talking about cube complexes, but you should see this kind of application. Hyperplane. Okay, and then there are other hyperplanes. There's there's one over here. That's a hyperplane. There's one here, and then there are probably more. Right? There's also this one, and maybe that's it in this case. Okay, so then you make a. So what is the contact graph? So the vertices are hyperplanes. Hyperplane. Right. So in this case, I would have 1, 2, 3, 4 vertices. And when do I put an edge? So edge corresponds to contact. Okay, so what is contact? So for example, if 2 hyperplanes intersect, then they contact. So this means either intersection or what's called osculation. Okay, so the osculation is something like this. So I have a. Okay, so here's osculation. I can have a. Here's a. So here's a hyperplane like this, and there's another hyperplane like this. They don't intersect, but they osculate. So if I take a natural tubular neighborhood of each hyperplane, so I just thicken each one of these mid cubes into the whole cube, then those neighborhoods intersect. Right? So here's the intersection of the. Okay. So osculation just means that the tubular neighborhoods intersect. But the
do you put a loop outside the vertex if the hyperplane self-osculate?
So it turns out it cannot self-osculate in the cat zero. It can self-osculate in the quotient, but not in the universal cover. So, but hyperplanes don't. Okay. And okay, so that's the contact graph, and then there is a theorem of Hagen that this x is hyperbolic, and not only that, it's actually quasi-isometric to a 3. So x is hyperbolic. In fact, quasi-isometric. If you don't know what quasi-isometric means, it just roughly speaking, it's like taking a tree and then making some kind of a thickening of it. It's not exactly a tree, but it's you can sort of pretend it is. It's only hyperbolic. Okay, so the point is that if you have a group acting on a cat zero cube complex, then it's also going to act on the contact graph. And so any kind of random walk on G can be projected not only to the cube complex but also to X, and then you have information. So for example, it could be that your group is something like you look at the Cayley graph or Cayley 2 complex of your group, and it looks kind of like this. There are these planes, perhaps. It's not hyperbolic. The group is not hyperbolic, and then there is edges coming out, and then to every edge. So maybe this is just the universal cover of something like take a torus and then attach a loop. Okay, and then the universal cover is going to have these planes that come from the torus, and these planes will be joined by edges to each other. Okay, so it's something like this, right? So schematically. Yeah, that's sort of the space. And the space is not hyperbolic. But I can, if I go through this construction, then essentially what will happen is that these planes will be collapsed to something bounded, right? If I take here's a cat zero cube complex. I just take I cover I make the plane into a cube complex by tiling it by these squares, right? So then I have then I have hyperplanes. There are vertical hyperplanes, and then there are also horizontal hyperplanes. And so my contact graph is going to have infinitely many vertices, but the diameter of this space is going to be what? 2, right? Right? Because any vertical hyperplane intersects every horizontal hyperplane. And so if I have 2 vertical ones that are far apart, I just have to take a horizontal one, and then we'll see that. Okay, so this is not very interesting here. This is just going to be some kind of a bounded thing. And but it does exactly what we want, because we'd like to convert this into something hyperbolic. This is not hyperbolic. But how do you convert it? Well, we have to kill these planes, because that's what's causing the non-hyperbolic behavior. And that's exactly what the contact graph does. It just kind of collapses these things with something bounded, and this becomes kind of a tree. Okay, it's not quite a tree, because instead of a vertex, you'll have something of diameter 2, but it's quasi-symmetric to a tree. And then this theorem is going to tell you about what the random walk looks like over here. And then you might not have any, if the random walk stays for a long time inside a plane, then you won't see that in the contact graph. But that won't happen anyway, right? That's very unlikely to happen. So the point is that this theorem gives you information even when the space where the random walk happens is not hyperbolic. Okay, so maybe that's enough propaganda of why this is good. And maybe I'll tell you now about the plane, and then maybe we'll take a little break and we'll try to get this. I have this little program about that illustrates random walk in hyperbolic plane. So if you can get that going during the break, that'll be good. Okay, so let me now tell you what the plan is here. Okay, so outline of proof. Proof of this theorem, Martiozzo theorem. Okay, so the first step is to construct something called a stationary measure. On the boundary of X. Okay. So the stationary measure, I mean, I'll introduce it more formally, but basically, what happens is that here's X naught, and you have these kind of random walks, and we know that it's only at the end of the theorem we know that that most of these will converge to a point, and so you can given a set in the boundary, you can think about the hitting measure. You can think about the set of sample paths that actually converge to some point in that set. Okay, so that's sort of a hitting measure. And this hitting measure has some formal properties. Even though you don't know, you don't even know that there exists a hitting measure. We don't even know that this converges. But there is a formal property that hitting measures satisfy. And all measures that satisfy this formal property are called stationary measures. And we just need to construct one of those. Okay, so we have to see that there are measures that satisfy the correct formal property of a hitting measure. Okay, so this is relatively simple if the boundary of X is compact. Constructing stationary measures on compact spaces is that follows from a famous theorem in functional analysis. Okay, so that's not very hard, but our problem is that boundary X may not be compact. That in the interesting condition in situations like, say, the curve complex and so on. When X is not locally finite, this boundary X is not going to be compact. So this is tricky when X is not locally finite. And so the main kind of a technical contribution of Mladen in this work is they make use of this Horo function compactification. So they make it compact. They force it to be compact. Okay, so so the solution is that you use the Horo function boundary. Okay, so I'll have to remind you what that is, and so what happens is that we'll construct the stationary measure on something compact, and then we'll have to argue that in fact it's supported on sort of an interesting subset of that compact space, and that interesting subset maps to the boundary of X, and so then we'll get the stationary measure on the boundary of X by pushing the stationary measure from the Horo function boundary. Okay, so that's probably almost half of the proof, I think, this first step. Okay, and then then what we want to do is show that for almost every sample path omega n, the sequence, so let's call this nu, stationary measure nu. So the sequence, so you push forward nu, this measure nu, by the sample path omega n, right? So omega n is some group element, and the group acts on the boundary. And so I can push it forward, right? So you can think of if I have an advanced, let's pretend this is hyperbolic plane. So I have some let's call it omega n x naught. So this element that takes x naught to omega n x naught, if this point is really close to the boundary, then you can think of this as being some kind of a loxodromic element that translates by a very large margin. This distance is large. And so what is that going to do on the boundary? Well, it'll take this the boundary, and it'll squeeze most of it into some small open set. And so that means that the measure that you started out with on the boundary here, that was maybe more or less uniformly distributed, will all of a sudden, when you apply this element, will be concentrated in a small set. And in the limit, it will actually converge to a one-point mass. So the sequence converges to, so in this step, we're only going to argue that it converges to some measure nu sub omega on the boundary of X. Okay, so here we kind of expect this to be a measure that's supported on a point. But in this step, we are just going to argue that it converges to some measure, and this is going to be essentially this famous theorem in probability called the martingale convergence theorem. Okay, and then the next step is going to be that for almost every omega, there's a subsequence. Say n sub k, so that if I just take that subsequence omega n k, so it's a subsequence of the sample path, and I apply it to x naught, that this sequence converges to some point in the boundary of X. So it could be that maybe I'm wandering all over the place, but after taking a suitable subsequence, it'll converge to a point. And then somehow you have to put the 2 and 3 together, and deduce that. So first of all, this measure. What is this measure? Well, that same measure has to work for this subsequence, which converges to a point. So you argue that this omega, this measure nu omega is really just a Dirac mass at lambda, and then conclude. So and then theorem follows. Because now well, I mean there are a few things you have to say here, but that basically this is it. Once you know that on the level of measures, the sample paths will bring this big measure will bring to a single point, then the theorem will follow. This is somehow. So these are the main steps. Right. Okay, so maybe this is a good place to take a break and then try to get this program going. So maybe like, I don't know, 10 minutes or something.